So, as we have mentioned, we have discussed just now that if f is differentiable to for the differentiability at the point AB, the necessary condition is that this equation is satisfied. So, what is this equation? This equation is in terms of the directional derivative duf at AB, which is equals to the gradient of f at that point times the unit vector. So that is nothing but u1 times fx at AB plus u2 times fy at AB. So this equation is satisfied if the function is differentiable and using the differentiability of the function using the gradient, we can find the directional derivative at that point. One problem we discuss is we started in the previous lecture is that if we have a function from R2 to R, which is defined to be fxy equals to x square y divided by x power 4 into y square, and we need to find the directional derivative of f at 0 0 in the direction of 1 1. So since 1 1 is not a unit vector, we divided it by its length, which is root 2, and then we have found the directional derivative of f in the direction of u, which is 1 by root 2 1 by root 2, is essentially, there is a typo here, this is u1, and then we have found that the directional derivative in the direction of u is 1 by root 2. So what we have not verified was the differentiability, right? Whether the function is differentiable or not. So what was the previous result? The previous result says that if the function is differentiable, then this equation is satisfied. So let us verify this equation. So to verify this equation, first of all, we need fx and fy at the given point. So the given point is origin. So let us find out fx and fy at the origin. So fx at origin is nothing but limit h approaches to 0 f of h0 minus f of 0 0 divided by h, and the value of the function is x square y divided by x power 4 plus y square. So by the definition of the function, if x or y is 0, then fxy is 0 function, right? The value of the function is 0 if either x is 0 or y is 0. So that will give us that this is nothing but limit h approaches to 0, f of h0 is 0 because y coordinate is 0, value of the function at origin is also 0 divided by h, and this is nothing but 0. Similarly, we can check the partial derivative with respect to y at the origin. So by definition it is limit k approaches to 0 f of 0k minus f0 0 divided by k, and again here the first coordinate of the function is 0 in f0k, the value of the function is 0 minus 0 divided by k, and that is equals to 0. So both the partial derivative of the function is 0, so therefore the gradient itself is 0. So the equation, so let me just write down what is the gradient. Gradient of f at 0 0 is nothing but fx at origin, fy at origin, and fx at origin is 0, value of fy at origin is also 0. So essentially the gradient at origin is nothing but the 0 comma 0. Now we will verify this equation. Directional derivative of u at f of AB is gradient times the unit vector. If the function is differentiable, then for every unit vector, this equation must be satisfied. So we will check this equation for u equals to u1 comma u2, which is 1 by root 2, 1 by root 2. We have already found the left side of the equation. So AB is 0, 0 here. So what is the directional derivative? That is 1 by root 2. And on the other hand, we have gradient of f at 0, 0 times the unit vector. So gradient we have observed that it is 0 comma 0, and the unit vector is 1 by root 2, 1 by root 2. So the dot product of this vector or the scalar product is nothing but 0 times 1 by root 2 plus 0 times 1 by root 2, and that is nothing but 0. So this condition, the necessary condition, is that the directional derivative must be equals to gradient times the unit vector, the dot product of gradient and the unit vector. But here we can see that the directional derivative is 1 by root 2, and the gradient for the same unit vector is 0. So therefore du at 0, 0 is not equals to gradient of f at origin for u1 comma u2 to be 1 by root 2, 1 by root 2. So therefore the necessary condition fails. The necessary condition fails means what we can conclude is, from this theorem we conclude that the function is not differentiable, right? Because if the function is differentiable for every unit vector, this equation must be satisfied. But for particular unit vector, that is 1 by root 2, 1 by root 2, this equation is not satisfied. So from this theorem we get that from the previous theorem, the function is not differentiable. So whenever the function is differentiable, this equation is satisfied. So this equation is not satisfied, that means function is not differentiable. But on the other hand, if this equation is satisfied for every unit vector u, that doesn't mean that the function must be differentiable. So converse is what I'm mentioning is that the converse of this theorem is not true. So even for every vector u, this equation may be satisfied, but the function may not be differentiable. So that can happen. So let us see one example. So we have a function f from R2 to R be a function given by fxy is equals to x cube y divided by x power 4 plus y square if xy not equals to 0 comma 0, and the value of the function is 0 if our point is origin. So the question is that check whether this particular equation is satisfied for each unit vector u is equals to u1 comma u2. Right, so in the previous example we have taken only the unit vector which was 1 comma 1. It was related to 1 comma 1, so the unit vector was 1 by root 2 1 by root 2. But for this particular example we need to take this condition for every unit vector. So that means the vectors u1 comma u2 such that u1 square plus u2 square is equals to 1, all such vectors. And the next question is whether the function is differentiable at the origin. So solution, what we do is we need to find the directional derivative at every unit vector, because any specific unit vector is not given. So therefore what we will do is we will start with the definition of the directional derivative, and we substitute the value of the function in that definition. Right, whatever function is given, the definition of function we'll use in the definition of directional derivative, and we will see what happens. So let u be u1 comma u2 be a unit vector. So therefore the directional derivative of u of the given function f at origin, by definition it becomes limit t approaches to 0 f of, so a comma b is 0 here, so a plus t times u becomes t times u1, then b plus t times u2 becomes t times u2 because b is 0, minus f of ab which is f of 0 comma 0 divided by t. So this is just the definition in terms of the vector u. Now in this definition we will just substitute the value of the function. So let us see what it becomes. The value of the function is x cube y divided by x power 4 plus y square. So let's substitute that. So we have tu1 power 3 tu2 divided by tu1 power 4 plus tu2 square, right, and minus f of 0 0 is 0, the whole term divided by t, the whole term divided by t. So let me just write down it before, so that we can write down in one page itself. So this is what we get by simply substituting the function itself in the definition of directional derivative. So now what we'll do, we will further simplify this. So if we further simplify this, it will become limit t approaches to 0 what we get is we get t power 4 in the numerator. In the denominator we have already one t outside, and the t square term will come from the denominator because t power 4 plus t square is there. So if you cancel all those terms, the finally the power in the numerator will be t, because t power 4 divided by t power 3 is t, u1 power 3 u2 divided by t square u1 power 4 plus u2 square. So just check whether we are correct or not. So we have cancelled the power t power 3 in the numerator and the denominator. So now we need to find this limit for all possible values of u1 as well as u2. So what we will do is we can take the cases either u1 is 0, u2 is 0. So it depends on what formula turns out to be here. We will simplify that by considering u1 is equal to 0, u1 not equal to 0, or u2 is equals to 0, u2 not equals to 0. Right. So what we know here is, we know that u1 u2 satisfies this equation because it is a unit vector. Right. So u1 square plus u2 square is equals to 1. So that means since u1 square plus u2 square is 1, u1 and u2 both cannot be 0, because if u1 and u2 both will be 0, then we'll get 0 is equals to 1, because left hand side will be u1 square plus u2 square, that is 0, right hand side is 1. So therefore u1 and u2 both cannot be 0 at the same time. So that means whenever u2 is 0, u1 is non-zero, basically its value is 1, and the other case is u2 is non-zero. So since our function has one term which is u2 square, which does not involve t, we are considering two cases. First case is u2 is 0. The other case we will consider is u2 is non-zero. So let us consider both the cases. So if in the first case u2 is 0, so then what is the possible choice of u1? So u1 u2 satisfies this equation, u1 square plus u2 square is equals to 1. So if u2 is 0, if we substitute that, we get u1 is equals to 1 there. So in the first case, when we have a vector u1 comma u2 in which u2 is 0, u1 must be 1, and in this case our directional derivative, that is this limit, in which we have to substitute u1 is 1 and u2 is 0. So what will be the limit? So in the limit u2 is 0, so u2 is this term, so it is 0. Similarly this term is 0 and u1 is 1. So what essentially we get is, we get 0 divided by t square, u1 is 1 and u2 is 0. So essentially what we get is 0, because it is limit of t tends to 0 of 0 term, and limit of 0 is 0. 0 is a constant. So in this first case, whenever we have a point u1 comma u2 in which u2 is 0, the directional derivative is 0. So on the other hand, if we have a unit vector u1 comma u2 where u2 is non-zero. If u2 is not zero, what will be the value of this limit? So we have the limit t approaches to 0, tu1 square, tu1 cube u2 divided by t square u1 power 4 plus u2 square. So let us write down that. So if we have this limit, let us just substitute t equals to 0. If we substitute t equals to 0 in this limit, what we get is 0 divided by 0 plus u2 square, and u2 is non-zero. u2 is non-zero, that means the denominator is non-zero of 0. So that means the value is 0. So what we have done here is, depending on what limit we are getting, of course in every example this is not possible because u1 square plus u2 square is 1. But after other than origin, we take the cases whether u2 is 0 or u2 not 0, or u1 0 or u1 not 0, depending on what limit we have. In this limit, why we have considered only u2 not 0? Because in this limit the term u2 square has no coefficient of t, right? So instead of this term, if we get the term of u1, then we can consider the other case. So what did we prove? We found the directional derivative for every unit vector u1 comma u2, and the directional derivative is 0 in all the cases, because whenever we have a unit vector whose second coordinate is 0, the limit is 0. The unit vector whose second coordinate is non-zero, in that case also the directional derivative is 0. And all the unit vector has only these two possibilities for the second coordinate. So it is irrespective of the first coordinate, whatever it is, depending on the second coordinate, we have found the limit for every u1 comma u2, and the directional derivative turns out to be 0 in every case. Right. Let us write down these. So therefore, for each unit vector u equals to u1 comma u2, the directional derivative of f at origin turns out to be 0. So now what we need to check, we found the directional derivative. Yeah.
सर u1 और u2 1/√2 नहीं हो सकते?
Yeah, if you take u1 and u2, both are 1/√2, then that will be the case of u2 non-zero.
Yes, sir.
Right, because u2 is 1/√2, and we already found the directional derivative when u2 is non-zero.
Okay, sir.
Right, so in that way we have found the limit for every vector, every unit vector.
Okay, sir.
Right, so depending on the last coordinate. So first thing we found that is required in the question, that is this part. Now we need to find this part, and for that part we basically need the gradient of f at origin, and that is partial derivatives fx and fy we need to find, at the origin to find the gradient. So let us, yeah. So note that the directional derivative. So what is fx? Fx also we can find using directional derivative, right? So in the last lecture we observed that fx is nothing but directional derivative in the direction of 1 0 of the function at origin. So now in this case, what is u2? U2 is the vector, unit vector is 1 comma 0. That means u2 is 0. u1 is 1, u2 is 0. And if u2 is 0, the directional derivative is 0. Anyway, all the directional derivatives are 0 for this function at origin. Similarly, fy at origin is directional derivative at 0 comma 1 of the function at origin. So here u2 is non-zero because u2 is 1, but still in that case also directional derivative limit is 0. So what we got is fx is 0, fy is also 0 at the
Mm-hmm.
origin. At the origin, yeah. So any doubt? Yeah. So both the partial derivatives are 0 at the origin. So that means gradient is 0 at the origin. So now what can we say about the equation? Whether the equation is satisfied or not? So which equation we are talking about? This equation. The directional derivative equals to the gradient times the unit vector. So let us just note that. So therefore, the gradient of f at origin is nothing but fx at origin, fy at origin, and that turns out to be 0 comma 0, right? And what does this gives us? So this gives us that the directional derivative at origin is 0 and gradient is 0. So that means whatever unit vector we multiply the gradient, that is nothing but 0 comma 0 times u1 u2. So this is 0 u1 plus 0 u2, and that is 0. For all unit vectors, whatever unit vector we take, since the gradient is 0, the gradient times the vector, the product is 0, right? So the right side of this equation is always 0. The left side, we already found that the directional derivative is 0 for every u, and therefore the equation is satisfied. So therefore, the gradient of f at 0 0 times u1 comma u2 is equals to duf at origin for every unit vector u1 comma u2, right? So now what we need to check, so let us go to the theorem. So theorem says that if the function is differentiable, then this equation is satisfied. So if the converse is true, then the function must be differentiable, right? So let us see whether the function is differentiable for this particular example or not. So For differentiability, what we need to check, the first thing we need to check is whether the partial derivative exists at that point or not. So that we already verified in this example, that fx and fy at origin, not only they exist, its value is 0. The first condition of the differentiability we already checked. The second condition, to verify the second condition, we need to check the limit of the function. So for differentiability, of f at origin, we need to check the following condition, following limit. So limit is that limit xy approaches to the point where we are finding the limit. So we are checking the differentiability at origin of the function fxy minus f evaluated at that point minus fx at 0, 0 times x minus x naught is x minus fy at origin times y divided by x minus x naught square plus y minus y naught square. So this condition we need to check at the origin to verify that the function is differentiable or not. So now what we'll do, we will just substitute the value of the function. So value of the function is, let us go to the definition again. So that is x cubed y divided by x power 4 plus y square when the point is not origin, and when at the origin the value of the function is 0. And also we know that fx and fy is 0 at the origin. So all these values we can substitute here. The value of the function is x cubed y divided by x power 4 plus y square. X power 4 plus y square minus value of the function at origin is 0, partial derivative of 0 is 0 times x minus 0 times y because fy is 0 divided by square root x square plus y square. So now we can just simplify this limit. What we will get is limit xy approaches to 0, 0 of the function x cubed y divided by x power 4 plus y square times square root x square plus y square. So now let us verify whether this limit exists or not. So what we will do first, so this is a limit of two variable function. So what we do is first we'll check the limit iterated limits, then we check the limit along y equal to mx. If all the limits are same, we'll go for the epsilon delta definition, right? If we can squeeze this function by square root x square plus y square or not, right? So here note that the iterated limits, what will be the iterated limits? So if we take x tends to 0, then y tends to 0, and y tends to 0, then x tends to 0, then both the limits will be 0. Right? Both the iterated limits will be 0. Further, along the path y is equal to mx, also the limit is 0, right? The limit is 0 along both these paths, but then if you go for the squeezing this limit, that is basically epsilon delta definition, then what we can observe is that x square plus x square minus y square is non-negative. So that means basically x power 4 minus 2x square y plus y square is non-negative, and that is nothing but x power 4 plus y square is greater than equal to 2x square y. If you use this computation, then what happens is x square y is less than equal to half x power 4 plus y square. So that means this term, so this you can do with AMGM inequality also, this one. So this thing is less than or equal to half times modulus of x divided by x square plus y square. And then we know that modulus x is less than equal to x square plus y square. So what we get is this is less than equal to half, but we don't get here the term of square root x square plus y square. So that gives us a hint that squeezing we cannot use here for this particular example. That means we need to find some other path along which the limit is different than 0. If we can do that, we can show that the limit does not exist. So how to find the third path? So to find the third path, sometimes it is helpful to see the denominator term. So here the denominator term is x power 4 plus y square. So if we compare this term x power 4 with y square, what we get is basically we get x power 4 is equals to y square. So let me just write down that. So in the denominator, we have term x power 4 is plus y square. So if you compare the powers, so in that case we get x power 4 is y square, and that means what we get is we get y equal to x square or y equal to minus y square, right? Basically we are getting the parabola. So along this parabola, let us try to find this limit. So limit xy approaches to 0 0 of the function x cube y divided by x power 4 plus y square square root of x square plus y square along the parabola y equal to x square. If we find this limit, what we need to do, we need to substitute y equals to x square in this limit. So if substitute y equal to x square, we get x power 4 plus x power 4 square root of x square plus x power 4. And now the limit is only in x variable, that means we will take x approaches to 0. So now if we take the square root x square common, what we get is limit x approaches to 0, x power 5, this will be 2 x power 4 square root of x square times 1 plus x square, and then we substitute. So this will anyway cancel because x is not equal to 0. So finally the limit turns out to be half because we are substituting x equals to 0. So therefore what we have shown is that along the parabola, if we approach to the origin, then the value of the limit is half. And if we approach along the line y equal to mx, the value of the limit is 0. So that means the limit depends on the path chosen. And therefore the limit does not exist. In this case, the limit does not exist, and since the limit does not exist, therefore the function is not differentiable. At origin. So this is an example where this particular equation is satisfied. The directional derivative equals to the gradient times the dot product of gradient and the unit vector. However, the function is not differentiable. So that means the converse of this theorem does not hold. So we have a couple of minutes. So let me just write down the statement of mean value theorem. For the two variable case.
सर आपने पावर्स कैसे कंपेयर की सर वो समझ नहीं आया.
Yeah, so just let me go again there. So
नहीं सर
in the
नीचे
yeah.
नीचे सर यहाँ पे एक पैराबोला की इक्वेशन आ गई थी वहां पे.
Yeah, so that is what I am saying. So it comes from this limit. So in this limit, what we are finding that function is x cube y divided by x power 4 plus y square root x square plus y square. So when the denominator becomes 0, so denominator becomes 0 if x square plus y square is it is 0. All right, something like that. So basically we are x square is equal to y square. If we compare this particular term, we get the curve x square equal to y square will give x equal to plus minus y. But that we already checked here for y equal to mx. So the other denominator, that is x power 4 plus y square. So in that term, if we compare x power 4 with y square, so that will give us the idea that x power 4 is y square, this equation. So now since x power 4 is y square, we take the square root. So we get either y equal to x square or y equal to minus x square. So we are checking at the first term. We can also
So do we have to make the denominator 0?
yeah, that is sometimes this gives a hint that what particular curve we need to consider.
Okay sir.
Right? Every time it may not work, but it is useful sometimes. Okay, so let me just write down the statement quickly. So we have a function from R2 to R. which is differentiable. And if we have 2 points in the xy plane, then there exists a point in the xy plane which lies on the line segment joining A and B. So in mean value theorem, in single variable case, we know that there is a point C in the interval A to B. But in xy plane, we don't have interval. So what we consider is we choose 2 points A and B in the xy plane, and we draw a line segment between them. So C lies on the line segment in A and B, and C is not equal to these 2 points. C not equals to A, C not equals to B. And C satisfies the condition that FB minus FA is equals to F dash C B minus A. Right. So what is A here? A is two coordinates, x naught, y naught. Similarly, B is two coordinates, x1, y1. And here F dash C is basically the gradient. Okay, so let us stop this lecture here.